And it's my special pleasure to be able to welcome you to this because as scientists at the Lagrange Institute, of course, we make lots of mistakes and we grapple with difficult questions. I look forward to this talk, which will tell us that making mistakes, in fact, can open doors. I now have a very special pleasure to ask Jean Audouze to introduce our speaker. Jean Audouze has far too many accomplishments for me to mention, so I will mention only that he is adding one more to his long list, which is that he is the translator of this book, which will appear next year in French. And as such, of course, is intimately familiar with the book and of course with the author. And so, please, Jean, thank you for introducing our speaker.
Okay, so good evening, and thank you very much, Ben, and I am very pleased to introduce Professor Mario Livio to you. So we know each other for some time, I should say. You started your career by being a professor in Israel for about 10 years, and then you joined the Space Telescope Science Institute for a longer period, I would say. So most of your career has been made in the Space Telescope Science Institute. And besides to be a very prolific astrophysicist, more than 400 papers, a lot of contribution in very different fields. Mario is also a writer of popular books, and there is one which is already out, which is Dieu est-il mathématicien, which has been published by Odile Jacob about 2 weeks ago, 2 months ago, and he has many other books than this one. I am going to say a few words about it, which is especially one which to say that what are the equations which cannot be solved, and many about almost 10 of this popular book, which is very well received in the English world. And 1 year ago, since nobody in French, the French publisher was not paying attention to his books, so with Michel Cassé managed to convince Odile Jacob to publish a translation of Dieu est-il mathématicien, and I convinced the CNRS edition and the title provisional is Fabuleuse Erreur. And just to finish, to say that you will see that not only Mario, as I said, is a talented researcher in astrophysics, but also he did a lot of research in history of science, and I am sure that he is going to unveil some mysteries, and I learned quite a lot by translating his book. Thank you, Mario.
Thank you very much, Ben and Jean. It's my pleasure to be here. Henri Poincaré has always been one of my heroes, so it is only very fitting that I will give this talk at Institut Henri Poincaré. I'm crazy about mathematics, so it's very nice to be here. I apologize for having chosen to speak in English, even though I do speak quite a bit of French, because I don't speak science in French. So if I were to give this talk in French, I would have to all the time miss words and things. So it's much easier for me to speak in English. Okay, while I was writing this book, people kept asking me, what is your book about? And I used to say, it's about blunders and it's not an autobiography. Now, why did I decide to write a book about blunders? So I will give you a very simple reason now, and I will give you a more profound reason towards the end of the talk. The simple reason is that it is really comforting for the rest of us to know that even the most brilliant scientists have made some serious errors. And the scientists I discuss in this book are truly brilliant scientists. Let me just tell you that I discuss in the book 5 different people. I will only talk about 3 of them here because there isn't enough time. The 5 people I'm going to talk about are Charles Darwin, Lord Kelvin, Linus Pauling, Albert Einstein, and Fred Hoyle. Now, most of these names are probably familiar to you, with possibly the exception of Fred Hoyle, who was one of the most important astrophysicists of the 20th century. How did I choose these people? So I'll just give you a feel for that. So, first of all, I didn't want to go too far back in history. Because you see, you go too far back, for example, if you take somebody like Aristotle, who no doubt was a huge genius. But if you look at what Aristotle did in physics, there isn't one thing that he said in physics which was correct. So, you know, it doesn't make any sense. But of course, against the background on which he worked, you know, he was still a genius. So I only went to the middle of the 19th century. There is also a thread that connects my 5 scientists, and that is through the word of evolution. And by that I mean evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So this is the concept that goes through all my people. One other choice that I've made was that instead of making a laundry list of all the mistakes that every one of these 5 people made, I chose to concentrate on one blunder for each one of these people. Okay, now let's start. The first thing you notice about life on Earth is how diverse it is. You know, it's enough to go outside here during the day. You will see birds, insects, plants, people walking their dogs, and so on. Nobody actually even knows for sure how many species there are on Earth. The latest serious attempt to put a number of that puts it at 8.7 million species. But estimates range all the way from 5 million to about 100 million. And there is a reason why it's so uncertain because, well, first of all, they discovered new species every year. But also, you know, you just take a teaspoon of dirt from under your feet and there are thousands of species already there. So, in the millions. The second thing you notice about life on Earth is an incredible degree of adaptation and also this, you know, sort of scratch my back and I'll scratch yours type relationship, which we call symbiosis. For example, you know, I don't know, you look at the bee, and the bee has precisely the size that it fits into the flowers on which it feeds, and then the bee gets all this pollen on its body and it transfers it to another flower and all that and so on. Here in this case, this is this clownfish. It lives among the poisonous tentacles of the sea anemone. The fish protects the anemone protects the fish. The fish has this special mucus on its body that protects it against the poison of its host. All of this incredible degree of adaptation. These 2 facts, the fact that there are so many species and that there is this enormous degree of adaptation, has convinced many, many naturalists over centuries that there must be some guiding hand and this and that and I don't know what. And all of that changed in one blow in 1859 when this gentleman, shown here at old age, Charles Darwin, published his book on the origin of species by means of natural selection. Just as an aside, I'll note that when I write books, I actually like to go to the places where the people I describe worked and so on. So in this case, I also went and I actually held in my hand the very first copy of On the Origin of Species. And it does give you a special feeling. I mean, even in an age where you can find anything on your computer screen, still to hold in your hand the very first book is nice. So this particular drawing here, I put it here only because it is very beautiful from a graphics design perspective, not because it is correct. It actually isn't correct, and I'll tell you why. It isn't correct because it gives you a little bit the impression that things here are more evolved, let's say, than things here. And that's not actually true. You see, evolution is not like a ladder. Evolution is more like a bush. Things evolve in different directions. But things that are at the same distance from the beginning are equally evolved. So this drawing is a bit misleading, but it is still nice as a graphics design. Now, there is one thing that Darwin never published, and that's his genealogy trees. You know, like this. He never published, not a single one. But he still drew them in his notebooks. And I held this page again from his notebook. He never published them, but to help himself think, he did draw them. And I like this one in particular because you see it has primates down here and it has men up there. So, so he did like to do this to himself as an exercise, but he didn't actually publish them. Now, what is this theory of evolution by means of natural selection? The theory depends on 4 pillars, and those 4 pillars are supported by one grand mechanism. Now, this drawing here has absolutely nothing to do with Darwin's theory of natural selection. It actually comes from a Hindu myth. However, look, it has 4 pillars and are supported by one grand mechanism, so I thought it fits here. Now, there is actually a story related to a drawing like this. The story is almost certainly apocryphal, namely it's not true. But it is such a good story that I will tell it to you nevertheless. You know, there is in Italian a proverb that says, "Si non è vero è ben trovato," which means even if it's not true, it's a good story, basically. So I will tell you this story. So the story is that Bertrand Russell, the famous philosopher and mathematician, gave once a talk, and he used a drawing like this. And some lady in the audience asked him, "Yeah, but on what does that giant turtle stand on?" And he said, "On another giant turtle." And she asked him, "On what does that turtle stand on?" And he says, "Another giant turtle." But she insisted, "On what does that turtle stand on?" So here he lost his patience, and he said, "Lady, I'm afraid from there it's turtles all the way down." So it almost certainly didn't happen, but it's a good story nonetheless. Now, what are these 4 pillars? The 4 pillars are evolution, gradualism, common descent, and speciation. Let me explain those. Evolution. That's the concept of evolution itself. Namely, Darwin tells us species didn't always exist. They are not immutable. What we see today are not species that were always there. In fact, most of the species that ever existed have become extinct. What we see today is only the species that evolved from those. That's this concept. Second is gradualism. Gradualism is a concept that Darwin borrowed from his geologist friends. In particular, he was a personal friend with Charles Lyell, who was the greatest geologist of the time. So you see, in geology, they learned and they discovered that all the changes at the surface of the earth happen very, very slowly. You know, the wind and the water and the sun and this, they change the surface of the earth very slowly. And Darwin says, too, evolution also happens like this. It's not that you're going to sit there and watch a species turn into another species. It takes tens and hundreds of thousands of generations for that to happen. So that's gradualism. Then there is the concept of common descent. Common descent is the idea that all these species we see today on Earth, they all started from one life form. That's what Darwin tells us. Now, this is a powerful concept because, you see, what that means is that you know, there are people, I have a friend, Jack Shostak, who does these experiments at Harvard about origin of life. Namely, how did chemistry become life suddenly, yes? This is actually only possible if you are talking about one origin, basically, for this. Not that everywhere there is something completely different. So that's common descent. And finally, there is speciation. Speciation is, you see, Darwin was aware of the following problem. If it all started from one life form, how come we have today the millions of species? So he says, okay, that happens because of speciation. What does that mean? You have a certain species, and then it splits into two other species. And then that splits into two other species. And at every node like that, you split into two species. And since at every node you double the number of species, very quickly you get to huge numbers. So that's the idea. And he drew this in his notebook again, you know, this drawing of how speciation happened. Again, I like this page a lot. I don't know if you can see this from where you sit, but at the top of this page he writes, I think. You see, Darwin was very humble at that stage of his life. He didn't claim that he knows everything. He thinks. Now, all these four pillars, I said, are supported by one grand mechanism. What is that grand mechanism? That is natural selection. There is a philosopher at Tufts University. His name is, what's his name now? It will come to me in a minute. Daniel Dennett, who wrote once that he thought that the idea of evolution by means of natural selection is the greatest single idea that anybody has ever had. Now, this may be a bit of an exaggeration, but it is certainly an incredible idea. What's the idea? Like all great ideas, it is very simple once it is pointed out to you. It says like this. Suppose I have a certain species. And suppose that certain members of this species have a certain advantage in terms of coping with the environment, fighting predators, and producing offspring. Okay? If that happens, Darwin tells us, then over many, many generations, the whole population is going to shift towards that characteristic that gives it the advantage. Is that clear? I mean, if the members have a certain characteristic that gives them this advantage, that they can cope with the environment better and they can produce more children, then over many, many generations, everybody will have that characteristic. That's the idea of natural selection. Now, we have some examples for natural selection. So, for example, in England of the 19th century, there was this light-colored peppered moth, you see? And this light-colored peppered moth was so well camouflaged that, look, you can probably barely even see it here. You see it? It's right here. But then, in 1848, you know, there was the Industrial Revolution. They started pouring enormous amounts of soot into the atmosphere, which blackened all the trees. At that point, this light-colored peppered moth started sticking out like a sore thumb. It became the target of massive predation. And it almost became totally extinct. But at that point, this melanic version, this dark version of this peppered moth developed and started thriving, because that was now well camouflaged. Now, luckily for this light-colored version, even in 19th century England, they adopted somewhat greener practices, and it was saved from complete extinction. Okay? This here just shows a few rat snakes and how they adapted to their surroundings in terms of color and all that, you know, by natural selection. Now, look, from what I told you until now, I told you that Darwin came up with this incredible theory of evolution by means of natural selection, which explained essentially everything about life on Earth. So where is the blunder? So the blunder has to do with heredity. And let me explain that. You see, Darwin didn't know any genetics because nobody knew genetics at the time. Okay? So Darwin adopted the theory of genetics, of heredity, it was not called genetics, of heredity that existed at the time, which was that the characteristics of the mother and the father are mixed in the offspring in the same way as you mix paints. Okay? That was the theory. Now, this is not a blunder because Darwin didn't know any better. That was the theory. That in itself, adopting this is not a blunder. The blunder was in that Darwin didn't understand, at least at first, that if this were the correct theory of heredity, evolution by means of natural selection could never have worked. Not at all. And let me try to explain that. Look, imagine that you have a population of 1 billion butterflies, and they are all white. And there is one that is black. And imagine that black is that characteristic that gives you an advantage in terms of coping with the environment, producing offspring, and everything. Darwin's theory tells us that over many, many generations, the whole population of butterflies will turn black. That's what the theory predicts. Now, what would happen under blending heredity? The black butterfly will mate with a white butterfly, we will mix the colors like paints, and they will produce a gray butterfly. Black has in fact disappeared from the population and will never return again. The gray butterfly will mate with another white butterfly, and it will produce a paler shade of a gray butterfly. That one with another white butterfly, an even paler shade of gray. Very quickly you will have more than 50 shades of gray. But you will never see black again, while the theory predicted that it will be black, right? So this clearly cannot work. It's, you know, everybody who drinks gin and tonic knows this. If you have a glass of gin and somebody keeps pouring tonic into it, at the end you will not feel the gin. That's it, right? So it couldn't work. How does genetics really work? This was explained to us by Gregor Mendel. I remind you, Gregor Mendel was this guy who did experiments with peas, green peas, yellow peas, got a ratio of 3:1, blah, blah, blah. But what is the main point? The main point that Mendel told us is that heredity doesn't work like paints. You don't fuse the characteristic together. It's more like shuffling cards. You see, if you shuffle cards and I have an ace, and having an ace is good, it doesn't matter how much I shuffle, I would still have the ace. That's the idea of Mendelian genetics. So look at the difference between blending heredity and Mendelian heredity. In blending heredity, you can have one parent that has, let's suppose capital A gives the color black, lowercase a gives the color white. You get from one parent this, from the other parent that, they give gray. So far, so good. The bad news is that in blending heredity, the capital A and the lowercase a's cease to exist. They are fused together to some new thing. And that's it. And now going on, you will just see paler and paler grays. What happens in Mendelian genetics? You still get from one parent capital A, from lowercase a white. It would still produce gray. But the capital A and lowercase a's continue to exist. And then from here, from one parent, you can get this or that. From the other parent, you can get this or that. And depending on how those combine, you can get black, gray, or white. And if black gives you the advantage, then eventually the whole population can turn black. The reason I look all the time down is that there is a small step here, which I keep thinking that I'm going to fall at one point, because you can hardly see it. It's a low step. Okay, so that's the story here. You see, I cannot stand in one place. I have ADHD, so I have to walk all the time. How do you say ADHD in French? Probably the same letters, but in some other order, right? Like ADN instead of DNA or something. Or yeah. Okay, now, even though Darwin made this mistake at first, he actually was never happy with blending heredity. And how do we know this? You see, already in 1857, this is 2 years before the publication of The Origin of Species, he wrote once that he believes that propagation will turn out to be some sort of a mixing like cards and not true fusion like paints. He had this idea, but he didn't know. And then, in 1866, he wrote to Wallace, who was his colleague, a fantastic letter where he noticed something that, you know, you look at this today and you say, how is it possible that nobody thought about that then? He said, look, if heredity is by blending, how is it possible that every female of the world produces a distinct male and a distinct female and not some intermediate hermaphrodite? So he realized that there was a problem, only he didn't know quite how to solve it. So that was the thing. Now, there is a little story here that I will also tell you because it's kind of interesting. You see, when Darwin wrote this, this was 1866. There have been no fewer than 4 books that claimed that when Darwin wrote this, it was not because he himself had this insight, but because he read Mendel's paper. Mendel's paper was published in 1865. Now, this is the kind of thing that is not really important, but which sometimes drives me crazy. And I became obsessed with finding out whether Darwin indeed knew about Mendel's paper or not. Luckily for me, Andrew Sclater from the Darwin Project already did some work on this before me, so I could rely also on his work. And what did he and later I discovered? First, Mendel's paper was not in the possession of Darwin at the time of his death. We have every single piece of paper that Darwin had at the time of his death. He didn't have that paper. That's not surprising because Mendel's paper appeared in the archives of the Academy of Brünn, to which Darwin was not subscribed, so there was no reason for him to have that. Okay, but some of those books that claim that he knew about Mendel will tell you that, yeah, but he had some books that described Mendel's experiments with the peas. And it is true, Darwin had 2 books that described Mendel's experiments. Now, one of them described it so briefly that it was impossible for Darwin to figure out what was going on there. The second book, I asked for it to be brought to me. It was this book by one Wilhelm Olbers Fouquet. You see, Darwin has his name up here. This was his book. And indeed, it describes Mendel's experiment. Do you know where it describes Mendel's experiments? Here, in these uncut pages here. You see, you may remember that there were once books that you had to cut the top. Darwin didn't cut the top of any of the pages of this book. He never read this book. Not only that, it turns out that even had he, because I now read what Fouquet wrote, and had he even read what Fouquet would have read, it would not have been much illuminated, because Fouquet himself did not understand the meaning of Mendel's experiment, so it would not. So Darwin did not know about Mendel. Mendel, by the way, knew very well about Darwin. He had a copy of On the Origin of Species, which he annotated, underlined things, and so on. He wrote some quotations from it and so on. So Mendel knew about Darwin. Darwin did not know about Mendel. The second person I want to talk about is Linus Pauling. Linus Pauling is the only person ever to have gotten 2 Nobel Prizes without sharing them with anybody. 2 Nobel Prizes by himself. Madame Curie, you know, we are on the Pierre and Marie Curie street here. Madame Curie got 2 Nobel Prizes, but she shared them. Linus Pauling, 2 Nobel Prizes without sharing. One was for peace, but one was for chemistry. Without sharing, anyone. Here is Pauling in middle age, pointing to his model of proteins. Pauling became much older, but the model stayed the same because it was a correct model. So this was the correct model. How did he come about with this model? In 1948, Pauling was in Oxford on sabbatical. He was sick in bed, and he was trying to determine the structure of this molecule. Now, Pauling had his own methods. You see, at that time, people already have developed the method of X-ray diffraction. X-ray diffraction basically says, I want to study the structure of this molecule. I shine X-rays on it. And from the way that the X-rays are scattered, I try to determine the structure of the molecule. Okay? Pauling did not work this way. Pauling first used structural chemistry, which meant he knew the length of the bonds, and he knew the angles between the bonds and all that, and he tried to construct a model from that. And then at the end, he did X-ray diffraction to test his model. So rather than starting with the X-ray diffraction to determine the model, he did the model from his knowledge of chemistry and then tested it using X-ray diffraction. In this particular case, Pauling, for various reasons, managed to convince himself that this carbon and nitrogen and the 2 atoms that connect to them have to be in one plane. And then he started folding, you can see even folds here, started folding the paper to see how he can make a structure of the molecule. And eventually he came up with this model, which he called the alpha helix. And this was, of course, a very elaborate but very, very clever model that he thought was the model for these proteins. He was very happy with this, except for one thing. In his model, the distance between 2 turns was 5.4 angstroms. 1 angstrom is 100 millionth of a centimeter. It doesn't matter, 5.4 in this unit. And the X-ray diffraction images showed some structure as 5.1 angstroms, not 5.4. Now, you may think 5.4, 5.1, good enough for government work, you know. But Pauling was unhappy. He was so unhappy that he did not publish his model for 13 years. For 13 years, he did not publish his model. And during those 13 years, he did everything possible to test his model. First, he asked 2 other people, including Branson, to test whether there were other mathematical solutions. They actually found that there was one, which he discovered himself previously, which he called the gamma helix. But it was a bit too tight. It couldn't be a correct model. So he was left only with the alpha helix. Then he asked his assistant, Robert Corey, to do X-ray diffraction on pieces of the molecule and to test and so on. At the end, after 13 years, he convinced himself that this has to be the correct model. He published it. It turned out to be the correct model. This 5.1 turned out to be a little bit of an artifact because there is a coil inside the coil, and that produced something that's a little bit displaced. So he was very happy with this. Then he turned his attention to DNA. ADN. Now, in 1948, long before the structure of DNA was discovered, Pauling made the following very insightful statement. You see, we were talking about what is the molecule that replicates itself to form life. So Pauling noticed the following. He said, look, for everything that needs to replicate itself, it is easiest if it is composed of two parts that precisely complement each other. Because if that's the case, if I have half the molecule, I already have the other half automatically. So this was a very, very clever point that he made, and I wish he would have remembered it later, but as you will see, he has forgotten. The second thing he knew is something called the Chargaff rules, after chemist Erwin Chargaff. Now here is the point. It was already known in Pauling's time that DNA is composed of three main components. There are sugars, there are phosphates, and there are four bases, which for short were called A, T, C, and G. Two of them had a single ring to them, and two had double rings. So phosphates, sugars, and four bases. Now what Chargaff discovered was that in every piece of DNA that he took, the number of A's was equal to the number of T's, the numbers of C's was equal to the number of G's. This also seems to indicate some sort of a two-side structure, right? A equals T, C equals G, something like this. Yet, when Pauling finally came up with his model for DNA, it was a disaster. It was a total disaster. First of all, it had 3 strands in it. 3. How do you do complementarity with 3? Crazy. Second, he had the bases outside and the phosphates in the middle. Now, the phosphates are negatively charged. So they repel each other. Two negative charges repel each other. So the structure cannot hold. It would completely fall apart. So it was something like this. Here. Here was the structure with 3 things. The phosphates, these are the bases on the outside. The phosphates in the middle, or negatively charged, pluck. This will just make the thing explode and fall apart. Like that. Here. Okay. So it didn't hold. So what did Pauling say? He said, oh yeah, but I will put in some hydrogen bonds, some hydrogen atoms that hold it together. But that cannot be. You know why? So DNA is called a nucleic acid, right? Now we learn in, I don't know in which school we learn this, in elementary school, that an acid is something that if you put it in water, it releases its hydrogen. Now, how can it release its hydrogen if hydrogen is supposed to hold the whole structure together? Crazy. Third, what about the Chargaff rules? A equals T. How do you get that with 3 strands and I don't know what? In other words, Pauling had a model that was built inside out, had the wrong number of strands, and didn't obey the basic rules of chemistry. And this was the greatest chemist of the world. So what happened here? So one of the things I've done in Brilliant Blunders was to try to get into the heads of these people and find out, you know, why they made the mistakes they made. Now, this is not easy, yes? First of all, they're all dead. Pauling is dead. So I couldn't speak to Pauling, but I actually did speak to every postdoc or grad student that he had at the time and that is still alive. Okay? So there were three basic questions. I discussed this in more detail in the book, but there are three basic questions I wanted to find answers to. One is, why the rush? And what I mean by that. I told you that Pauling took 13 years to publish his model of proteins. Do you know how long he actually worked on his model of DNA before he published it? Can you guess? 1 month. He published his model after working 1 month on it. What happened? Why the rush? Second, what about the Chargaff rules, which he knew about? We know that he knew about. His model did not obey the Chargaff rules. And finally, what about the basic rules of chemistry? His DNA was not an acid. What happened? So I'll just give you a flavor of what I think are the answers. First, why the rush? Pauling, as much a genius as he was still human. And he was afraid that somebody will scoop him. Not Watson and Crick. He barely knew that they exist. But he knew that both Maurice Wilkins in London and Lawrence Bragg in Cambridge had better X-ray diffraction images of DNA than he had. And he was afraid that they will publish before him. So that's why he rushed. What about the forgetfulness? How did he forget the Chargaff rules? That's harder. I can only give you a guess, which makes Pauling even more human. And that is, Pauling couldn't stand Erwin Chargaff. They were once on a boat together from the US to Europe, and Pauling was a quite laid-back individual. Erwin Chargaff was a very intense individual. He kept bumping into Pauling on the deck of the ship and bother him with his rules and things. I almost think that Pauling took out of his head anything that had to do with Erwin Chargaff. Third, what about rules of chemistry? Now look, Pauling did not forget the rules of chemistry. He wrote the book on that, for heaven's sake, literally. So why is that? I think that here he simply fell victim to his own previous success. Namely, what happened with his model for proteins? His model for proteins showed him that his very first hunch was the correct model, and that everything later just confirmed it, and the rest turned out to be minor details that could be sorted out later. He thought he had the correct model, and that everything else is details which will be sorted out later. So he basically decided to gamble, but he lost. The correct model, of course, was found by Watson and Crick. DNA is a double helix. The bases are inside, such that A connects with T, C connects with G, which automatically explains the Chargaff rules, and also has precisely the complementarity that Pauling was talking about. You know half the molecule, you get the full molecule. Now, what did Watson and Crick do once they discovered the model? Watson was in his 20s. Crick was in his 30s. They did what two young such people do. They went to the pub. And the pub is the Eagle Pub in Cambridge, which still exists. It's a wonderful pub. And this is the place, they have now a plaque on the wall there. This is the place where Francis Crick stood in the middle of lunch and said, "We discovered the secret of life." Anybody who has been to Cambridge has once at least been to the Eagle Pub. It's a nice pub in general, and it also has this ceiling where RAF pilots used to go on missions in World War II, and they wrote their names on the ceiling there, and So it's a wonderful place. Now, I showed you Pauling when he was middle-aged and old. I showed you Watson and Crick when they were young, so here are when they are old. Now, since then, unfortunately, Francis Crick passed. Jim Watson is still alive. And actually, I spoke to him several times while writing the book. I put this picture here. It's from a meeting of proteins that Pauling organized in the 1950s. And I put it here for three main reasons. One is there are lots of Nobel laureates here. John Kendrew, Maurice Wilkins, Max Perutz, Jim Watson, Francis Crick, Lawrence Bragg. Lots of Nobel laureates in this one image. That's one. Number two, only one woman. Beatrice Magdoff from the Brooklyn Polytechnic. You go to a meeting on proteins today, it's about 50-50. So things have changed. Third reason, this was a science meeting, not a business meeting. Now, look at these guys. They all wear ties, for heaven's sake. You go to a science meeting today, nobody wears a tie. So things have changed. This is Pauling himself, by the way, and this is his assistant, Robert Corey. I go to my third person, which is Albert Einstein. This is the photo of Einstein which I like best, especially because when my hair is a little bit longer, it looks just like that. And I like to say that that's not the only similarity. What I say is, you see, Newton is dead, Einstein is dead, and I also don't feel so well. So Einstein, of course, has done many things. Among other things, he has done general relativity. And this is from a letter. His paper on general relativity was published in 1915. This is from a letter he wrote to an astronomer in 1913 already, and described how gravity should bend the light of a distant star. Now, here is Einstein's equation of general relativity. Now, some of you, I imagine some of you are physicists and know about this, but some of you may be a little bit rusty on your general relativity. So I will just describe to you the essence of this equation. Forget for a second this term here. What is written here? This thing here simply describes the geometry of space-time. The geometry of space. This thing here describes the energy and mass content of space. And this is the strength of the gravitational force. So what does this equation tell me? It tells me that the mass and energy that is in your space determines the geometry of that space, and that gravity is nothing but a curvature of that space. In other words, gravity is not some mysterious force that acts across distance. It is basically, imagine that I'm standing on a trampoline. I'm causing that trampoline to sag. If I now take some small balls and throw them onto this trampoline, the balls will find the shortest path in this warped space. What Einstein is telling us is that gravity is the same. Namely, the sun, for example, warps space in its vicinity, and the planets just find the shortest path in that warped space. That's what gravity is all about. It's the curvature of space caused by masses. In other words, masses tell space how to curve. Space tells the masses how to move. That's it. That's the essence of general relativity. Now, so Einstein wrote this in 1915. But then in 1917, he tried to apply his theory to the universe as a whole. Now, at the time, in 1917, they still did not know that there are other galaxies other than the Milky Way. but they knew that there are stars. Okay? Now, Einstein thought, because he thought it was more elegant, that all these stars should be in equilibrium, fixed. Okay? But he said, but wait a second, how does this work? You see, if every star attracts every other star, then this thing is not going to stay in equilibrium. It will collapse under its own weight. So how can you do that? Now, because he wanted everything to be in equilibrium, he added this term here, which includes this thing which is called the cosmological constant. And what the thing did is the following. Suppose I look at this point. If at this point gravity has a force in this direction, what that term does is it does a repulsive force exactly in the opposite direction with the same strength, so that to hold everything in equilibrium. So at every point, okay, this is attracted to here, I put a force here that will exactly balance that. That's the idea of that term there. Now, it turns out, by the way, this was not an excellent solution, because even though it created an equilibrium, it was actually an unstable equilibrium. It's a bit like me trying to balance this on my finger. Yeah, I can do this, but the slightest perturbation will cause it to fall, okay? But in any case, he was happy with it. He added that term, and he was happy with it. But then something happened. In the late 1920s, these two gentlemen, and there is a whole story there in the book which I will not go into now, this Belgian cosmologist and priest Georges Lemaitre, and following him, this astronomer Edwin Hubble, discovered that the universe is not static, it is expanding. The universe is expanding. This was discovered in the late 1920s. When Einstein heard that the universe is expanding, he said, wait a second. If it is expanding, then I don't need everything to be in equilibrium. Like, you know, if let's say I take this key and I throw it up, it's not in equilibrium. But what happens is that the gravity just slows it down. Yes, it moves and the gravity slows it down. In this case, it pulls it at the end back. But it's not in equilibrium at any point. So he regretted having put that extra term in his equations, and he pulled it out of the equation. There is again a question of whether he called it his biggest blunder or not. I'm afraid you'll have to read the book to find out whether he said that or not. September, the book will appear, not a problem. In French. If you can read Czech, it's already in Czech. So he took it out of the equation, and he regretted ever putting it back in. Okay? However, in 1998, two groups of astronomers working independently discovered that not only is our universe expanding, the expansion is not slowing down. It's speeding up. It's like it's accelerating. It's like me taking this key, throwing it again up. Not only it will not slow down, it would start accelerating towards the ceiling. You know, I once gave a talk about this particular topic to an audience. There was a 7-year-old kid who was sitting in the front row. And I said, what would you think if you saw these keys, or I don't know what I threw up then, accelerating towards the ceiling? And the kid said, magic. So it's like magic, you know, what is causing this acceleration? Well, we call it today dark energy, whatever. But you know what we think is the thing that is causing this acceleration, the universe to speed up? It's exactly that term that Einstein took out of his equation. So if Einstein did any mistake at all, it was not putting that term in. It was taking it out. You know, some people, they are so smart that even when they make a blunder, it turns out to be a big insight. So that's what happened in this case. Actually, had he not taken it out of his equation, Einstein could have predicted that the cosmic expansion should accelerate. Okay, with this I have finished what I want to say about my three scientists, but now I want to go back to the question of blunders and the real reason why I decided to write about scientific blunders. You see, one of the things that happens in school, at universities, and in the presentation of science in the media is as if progress in science is a direct march to the truth from A to B. You know, Newton sat down under the apple and, oh, sorry, it's because I have this thing in my pocket. Newton sat down under the apple tree, an apple fell on his head, he jumped up and said, of course, F equals gm1 m2 over r squared, you know. Now, anybody who is ever involved, not just in science, but in any creative enterprise, even artistic, you know, or literary or whatever, knows that nothing can be further from the truth. Progress in creative enterprises is a zigzag path with lots of false starts, lots of blind alleys, and lots of time when you need to go back to the starting point. That's how science progresses. Not only that, you see, we have developed a culture. I cannot speak about France because I'm not really that familiar with the French education system, but I can speak about the US. We have developed a culture where mistakes are not tolerated. But you know, guess what? We at the same time want people to think, you know, what we call outside the box, you know, to think in unconventional ways. Well, guess what? If you think in unconventional ways, you may make a mistake. But we want to encourage those types of mistakes. Namely, you will notice that my book is called Brilliant Blunders, not Sloppy Blunders. Mistakes that are done because you are being sloppy shouldn't be tolerated. Mistakes that are done because you are maybe not quite sloppy, but you are not thoughtful enough, you don't try to think about many possibilities, should not be tolerated. Even mistakes that are done because you are inexperienced are not good, because if you are inexperienced, you should have the courage to admit that you are inexperienced and ask for guidance. But we do want to encourage the mistakes that are occasionally done, not all the time. Yes, there is a lot to be said about incremental progress in science. That's how science progresses most of the time. But every now and then, you want people who will think outside the mainstream, in unconventional ways, and even if they make brilliant blunders. Yes? I'll tell you a story which some of you, or maybe many of you, know. How many of you know about, it's on the internet, you know, and so it's called the barometer problem. Do some of you know that? The barometer problem? You know that. A few know that. So let me tell you about that story. It's almost certainly another apocryphal story. I mean, it never happened, but it's a nice story. The story is about an exam in physics where students were asked, how would you measure the height of a very tall building using a barometer? And of course, the expectation was that the students will say that they will measure the air pressure at the top, air pressure at the bottom, and the difference tells you basically the height of the building. Now, one student answered something and was failed in the exam. And then he complained, the story goes, and a second professor was asked to talk to him to discuss the problem. So the second professor asked him, okay, give me an answer how you would measure the height of the building using the barometer. So the student gave him 10 answers, 10. And they were like this. One was, I'll drop the barometer from the roof to down and measure how much time it falls, and this is how I will measure the height. A second thing was, I'll tie the barometer to a string, and I will lower it from the roof, and I will then measure the length of the string. And the third was, I will take the barometer and put it against the wall and measure like this the height of the building in barometer walls. And the fourth was, I'll tie the barometer to a string and use it as a pendulum, and I'll measure the period of the pendulum at the top and at the bottom, and from the difference in the G, I will find the height, and so on. And my favorite answer is, I will go to the custodian of the building, and I will knock on his door, and I will tell him, look, I will give you this very nice barometer if you tell me the height of the building. So the professor asked the student, you didn't know what they want you to answer? And he said, of course I knew, but there is no reason why I should give you that answer. So this is what I mean by thinking unconventionally. Now, that story on the internet goes on to say that the name of the student was Niels Bohr, who was one of the greatest physicists of the 20th century. It probably never happened, but it's a wonderful story. So basically, let me finish here by saying that blunders in science and any artistic or creative enterprise, especially those that I call brilliant blunders, can actually be the portals to discovery. Thank you very much. I'll be happy to answer a few questions if there are. Are there any questions? Yes, please.
I have just one. You showed us 3 of 5 blunders, but these blunders are very of different nature. Namely, the one by Pauling is maybe the worst since he made really a mistake. While Einstein, I mean, it is not such a mistake. Yes. And for Darwin, he ignored, I mean, he had not in his...
it was a mistake.
Yeah, it was a mistake. But you see, so not only, maybe it is interesting to characterize the different type of mistakes.
Yes, so actually I specifically also chose different types of mistakes and different types of reactions to the mistakes by the individual scientists. And you're right, the one that looks perhaps the strangest is the one by Pauling, where it looks like it was a simple mistake, and why do I say it was brilliant, like I say about the others? But the reason I say it was brilliant is because it turns out that actually what Watson and Crick did is they adopted actually precisely Pauling's method of discovery when they discovered the correct model. And plus, Pauling, unlike some of the others, actually within a couple of months admitted that his model was wrong and accepted the Watson and Crick model. While, for example, Lord Kelvin never admitted throughout his entire life that he made a mistake, and even Einstein did not think he actually made a mistake. So, yes, you're right, they are all very different.
Juste ajouter que si vous êtes plus à l'aise en posant votre question en français, c'est évidemment, on comprend.
C'est OK, oui. Et si je ne comprends pas, alors il le traduit. Any other questions?
Yeah, I just had a question about Einstein's mistake.
Yes.
Because he added a term to have things in equilibrium. And this term actually meant that the universe is expanding, and so definitely not at the equilibrium. So...
Well, he thought it was not expanding. He thought it was in equilibrium. But his solution actually applied to a universe that actually could be accelerating, but he didn't realize this at the time.
Okay, so like it was a solution to, I mean, the solution was good for the both.
Yes, in principle it could apply to both, yes, yes. But the universe is actually accelerating, and yeah. But you see, he was treating the wrong problem too, because what is really expanding is the structure of space, and so the stars actually are not going anywhere. It's the galaxies that are really getting farther and farther from each other, but he didn't know that.
Thanks.
Any other questions? Don't be shy. This is your opportunity to ask questions. And if I don't know the answer, I will not be ashamed to admit that. Yeah.
You talked a little bit about what separates good mistakes that should be tolerated from undesirable ones.
Right.
I was wondering if you could say more about that, and also if you have any insights into what kind of incentives or environments are more likely to encourage good mistakes versus bad ones.
Yeah, this is a good question, and I don't know that I have an excellent answer to this, but let me give you some examples. You see, one thing that, for example, is done in the US a lot, and I don't know to what extent it's done in France, is that almost all exams are multiple choice exams. Almost all exams are given, you know, where you have 4 answers, you have to choose A, B, C, or D, okay? That's the common form of exam in the US. Now, there are advantages to this system, and the advantage is that exams like this are much easier to grade. Especially they can be graded automatically, yes? And the reason that that's good is that you can give more exams, and then the grade does not depend on the results of a single exam. I mean, you can give 10 exams instead of 1, and so there is something good about this. But there is also something very bad about this, which is the result is either right or wrong, and you never see the thought process of the person. So, for example, one thing that I would advise the educational system in the US, every now and then to give exams that are not multiple choice exams. And that would encourage these other things. Another example that I can give has to do with funding agencies. You see, in funding agencies, it has almost become, and I'm sure this is true in France as well as in other places of the world, you cannot almost propose something that you don't know the result already at some level. I mean, you propose things that you know you are going to get this or that result, yes? Only those things get funded. But what about, you know, those things that you don't know so much about what's going to happen? So for a while, they adopted a certain policy for telescope time, where they allocated about 10% of the time for proposals deemed risky. Namely, these were proposals that were well written, thoughtful, but where it wasn't absolutely certain that you can achieve the desired thing. I suggest that this kind of procedure should be adopted for many funding agencies, yes, that they will allocate a certain amount of time for risky proposals. You know, ones that maybe are not sure to give an answer, but that if they give an answer, this could be something really interesting. So that's another example. So these are just a couple of examples. Yeah. Whoops. I told you about these steps here, yes.
Returning on the category of blunders that Jean was mentioning, in which category would you grade things like cold fusion, for instance?
Cold fusion was definitely not a brilliant blunder.
Yes.
I think it was a sloppy blunder. Similarly, I can give you other examples of sloppy blunders. You may remember that a few years ago there were neutrinos moving faster than the speed of light, right? By the way, I'm on record. I went on public radio, national public radio in the US, and I said that if that result will turn out to be true, that neutrinos move faster than light, I'm going to eat my head. And I said, this is a stronger statement than you think, because I don't actually own a hat. So I promised to buy a hat and eat it. And it turned out to be a very sloppy kind of blunder. There was another blunder that I can name that was really sloppy, which was that, again, about 6 years ago or thereabouts, maybe 8 years ago, they claimed to have discovered certain bacteria that have arsenic instead of phosphorus in their DNA. Very sloppy experiment, okay? So these are all not brilliant blunders. If you want to talk about, you see, people tell me, why didn't you talk about Einstein not accepting quantum theory, for example? That was not a sloppy blunder. I mean, Einstein had very, very deep reasons why he suspected quantum theory, because, you know, it completely changed our view of physics from being predictable to something where you can only predict probabilities. And, you know, the EPR experiment, the Einstein-Podolsky-Rosen experiment, still people write papers about this today, even with the Aspect experiment and all that and so on. So that was, it was a blunder, no doubt, but I consider it a brilliant blunder. People ask me about string theory. Could string theory become a brilliant blunder? It certainly is brilliant. You know, there is no question about this. Even if string theory will turn out to be not the correct theory, yes, of quantum gravity, it certainly has taught us so much about the structure of a physical theory and has produced so many mathematical results that are incredible, that if it will turn out to be a blunder at all, which we still don't know, it certainly will qualify as a brilliant blunder, in my opinion.
Yeah, okay. So I would sort of back up what you say, but perhaps add another category which are not brilliant, but perhaps fertile blunders, blunders that you want to check the results, and then checking the result you end up by showing there's a mistake, but by the very process of checking, you learn something different.
Of course. Well, that's
so these
what
are
we
productive
do in science
blunders
all the
in a
time.
way.
Yeah. Okay. Maybe
Time
we'll
for
wrap it up.
one more question, final question.
Okay, thank you very much.
If not, then thank you again.